Okay, so here is a lecture on learning and memory. Key terms for this section: LTP and LTD. We'll discuss what those stand for. AMPA receptor and NMDA receptor, which are involved in the processes of LTP and LTD. Consolidation, implicit memory, declarative and explicit memory, and the Hebbian synapse, referring to Donald Hebb. And these are the learning objectives. Key differences between the different types of memory. The sequence of events leading to NMDA-mediated LTP. We'll discuss that in depth. And then talk about amnesia associated with hippocampal damage. What memories are lost, what types of memory are lost, and which ones are intact. So first, getting into the different types of memory. One type of memory that is not mentioned in your textbook, so it won't be on the exam, this is just an FYI, but just know there is one additional type than the ones we'll discuss, and that's sensory memory. So these are very briefly held representations of sensory experiences, visual and auditory, and they only hang around for a few seconds. There's a lot that's recorded here, but this is kind of the first. If you think of memory like a funnel, this is kind of where all those sensory experiences are collected, and then it's further filtered down. So there's a relatively small percentage of memories that make it past this first stage into short-term memory. So here's short-term memory, and we'll contrast this with long-term memory. Short-term, this is a limited capacity, and it's memory of events that just occurred. So it has a shelf life of a few minutes, and the magic number is 7 plus or minus 2 items that can be held in short-term memory. Now, short-term memory kind of is conceptualized like kind of a storage bin, where memories kind of sit there short-term, and they may get consolidated and make it to long-term memory. Now, the concept of working memory has kind of replaced this concept because working memory refers more to active maintenance of memories, manipulating them and doing things with them instead of just having them sit there in storage. So working memory is what you'll see more often discussed in the literature. There are different tasks for probing working memory. And when you're doing something like trying to remember somebody's phone number while you are looking for something to write it down on, then you're employing working memory when you're actively doing something with it. And there are certain groups of cells that oscillate while memory is held during this delay, while that memory is being used and manipulated. There are certain regions of the brain where you'll see oscillating rhythms. Long-term memory, by contrast, has a vast capacity, virtually unlimited, and these are memories that are held, as the name suggests, for long-term, longer than minutes, and could even be for the duration of your lifetime. So consolidation, this is consolidating, moving short-term memory to long-term memory. Donald Hebb, which we'll discuss in just a bit, who we will discuss in just a bit, he postulated that if you just store short-term memories for long enough, they're held in that storage area for long enough, then they'll become long-term memories. It's since been found that it's more complex than just the duration in which they're stored in there. So, for example, there are some memories that don't need to be stored and rehearsed for a long period of time. And they make it to long-term just fine. And then there are some that are stored for quite a while, maybe even days, but still don't make it to long-term memory, or still transient. Implicit versus explicit memory. This is Another way in which, well, this is long-term memories, different types of long-term memories. So explicit memories, these are declarative memories. These are things that are recognized as a memory, something that you can report and you're consciously aware of. Implicit means that they may still have some experience. They may still influence your behavior. Experiences can still influence your behavior, even if you don't recognize that influence consciously. One specific type of implicit memory is procedural memory. And this is when you talk about the memory of how to ride a bike. It's something that's stored long term, but it may be hard to consciously report. These are the motions that I go through in order to ride a bike. And so that would be an example. That's a classic example of procedural memory. You may recall the basal ganglia are an area of the brain that's involved in procedural memory. Another key term, Hebbian synapse. This is an image of Donald Hebb. This idea, or a Hebbian synapse, is one that follows this rule, that cells that fire together wire together. And this is a common phrase that you'll hear that still influences memory research. And in other words, this is saying that simultaneous activity in a presynaptic and a postsynaptic neuron leads to a more efficient synapse. So if you have a synapse that's getting used a lot, that increases the likelihood of both postsynaptic and presynaptic neurons firing an action potential at the same time. Simultaneous activity, that's going to lead to strengthening of that synapse, a more efficient connection. And this is, on the cellular level, what that is believed to look like. Okay, so this is the sequences of events involved in LTP. LTP stands for long-term potentiation. You can see there's kind of a lot going on here on this slide. There's a link to a video up here, which I'll post in the description to this video, that will walk you through this process. And I'll also walk through it here. I'll get to this figure here in just a second. So you have an axon here that's releasing glutamate, and the postsynaptic neuron has these two types of receptors, AMPA receptors and NMDA receptors. And this is just an FYI, AMPA and NMDA both stand for something. AMPA for alpha amino 3 hydroxy 5 methyl isoxazole 4 propionic acid. I can't even say it. And then NMDA for N-methyl D-aspartate. So both of these receptors are ionotropic receptors. Okay, so that means they'll let ions in. The AMPA receptor lets in sodium when glutamate binds to it. Okay, so if a little bit of glutamate is released, it's going to bind to the AMPA receptor. It also binds to the NMDA receptor. The AMPA receptor opens, lets in some sodium. The NMDA receptor would open and let in ions. However, there is a big magnesium ion that's sitting here in the pore, and it's blocking the channel. Okay, magnesium is an ion we haven't really discussed yet, but it is a positively charged ion. It's a 2+ charge. Okay, so if there's a minimal amount of activity in this neuron and glutamate's just being released, the only receptor that's going to open and allow ions to flow through is the AMPA receptor. Okay, so if the axon releases glutamate repeatedly, if you have strong activation of this axon, there's going to be a lot more glutamate released. Okay, that's going to activate lead to even greater depolarization in this postsynaptic neuron. Now, if this postsynaptic neuron becomes depolarized, this magnesium ion is going to sense that, and it's going to be ejected out because the positive charge in here has increased to the point that this positively charged ion is going to be repelled. When in the NMDA receptor then gets activated, now that the magnesium block is gone, it's going to allow sodium to enter, and also, this is key, calcium. Okay, so calcium is not only functions to depolarize, but it also functions as a second messenger. We saw that it provides a signal to vesicles to fuse with the membrane during synaptic transmission, for example. Calcium can signal a lot of different things to happen in a neuron. In this case, what it often signals, or this is one means by which LTP can take place, calcium is going to signal more AMPA receptors to be inserted into the membrane. Okay? So this is kind of showing that multiple are being activated, but the LTP that happens is when even more AMPA receptors are inserted in, and maybe they've already been synthesized. These are made of proteins, and so maybe they've been synthesized and they're just here ready to go in case that stimulation happens, that intense stimulation, and then they're going to be inserted into the membrane. Or it may signal the cell to produce some more. The end effect is that there are more receptors on the postsynaptic neuron to receive the signal. The next time this neuron, this presynaptic neuron, fires and releases glutamate, there's going to be more AMPA receptors to receive the signal, and it's going to lead to a greater depolarization in the postsynaptic neuron. Okay? Now, moving on to this figure here, you can see that here's kind of a baseline response. So these are EPSPs. And so this would be like figure 1, the baseline response, just small EPSPs. Then there's the simultaneous strong activation of 2 axons. This is that big stimulation event. And then afterwards, the EPSPs are of a greater magnitude. It's an enhanced response. This potentiation, or this enhancement of the EPSPs, is LTP, long-term potentiation. Okay. There is also LTD, long-term depression. We won't go into the sequence of events involved in this. Interestingly, it can also occur via NMDA-mediated mechanisms. But just know that it's the reciprocal process, long-term depression. Okay, it's not referring to clinical depression when you have a depressed mood. This is the reciprocal process in which synapses can be weakened, where AMPA receptors maybe are taken away from the postsynaptic neuron. Okay, I'm going to go ahead and pause this video and resume talking about, start another one talking about amnesia.